Good morning, everyone. Good evening, good afternoon, in whatever country you're joining us from. We're very pleased to see you here today. Thank you all for joining us for our inaugural Monash Prato Dialogue Distinguished Lecture Series in Artificial Intelligence. I'm Professor Joanna Batstone, and I'm the director of the Monash Data Futures Institute, and I will be your host and moderator for today. Before we begin, I wish to acknowledge the traditional owners of the respective lands on which we're in essence virtually gathered today. And I pay my respects to their elders, past and present. Please join us in today's conversation on social media by following us on Twitter at MonashDFI and by using the hashtag Monash Prato Dialogue. The Monash Data Futures Institute that you're joining today is the largest interdisciplinary community of AI and data science thought leaders across Asia Pacific, and we're committed to excellence and shaping the future of the field. Our focus areas include the use of data-driven AI across our research in governance and policy, sustainable development, and health sciences. This new Monash Prato Dialogue Distinguished Lecture Series aims to explore the evolving impact of data science and AI in society by fostering a global dialogue. This series takes its name from Monash University Center in Prato, Italy, and our center represents an international base for research, education, for intellectual and cultural exchanges, and it enables us to bring people together to meet, learn, and collaborate with peers and colleagues from around the world. Today, as we launch this new lecture series, we are delighted to welcome our inaugural world-renowned and distinguished AI researcher, Professor Stuart Russell. Professor Russell is a professor of computer science at the University of California at Berkeley, holder of the Smith-Zadeh Chair in Engineering, and director of the Center for Human Compatible AI. He's also an honorary fellow of Wadham College, Oxford, an Andrew Carnegie Fellow, and a fellow of IJCAI, ACM, and the American Association for the Advancement of Science. Stuart's a recipient of many awards and honors, including the IJCAI Computers and Thought Award, and he also held the Chaire Blaise Pascal Chair in Paris from 2012 to 2014. Now, of course, many of us will know Stuart from his book, Artificial Intelligence: A Modern Approach, co-authored with Peter Norvig. It's one of the standard texts used in AI, used by over 1,500 universities in 135 countries around the world. And in fact, many of us may well have been taught from this very book ourselves. In today's lecture on provably beneficial artificial intelligence, Professor Russell will ask, how will we, humans, retain power forever over entities like AI that will eventually be more powerful than ourselves? And that's enough of the introductions. I'm delighted to welcome Stuart today. Over to you, Stuart.
Thank you very much, Joanna. And thank you to the university and the Institute for inviting me and setting up this, this dialogue series of lectures. So I'm going to share my screen and show some slides to reiterate some of the points I'm going to be making. So let me begin by just reminding everyone about what AI is, or at least what the textbook says that AI is. And of course, it means making intelligent machines. And what we have meant by that, pretty much since the beginning of the field, is that machines are intelligent to the extent that their actions can be expected to achieve their objectives. And this formulation, which is in many ways borrowed from notions of rationality that had already emerged in philosophy and economics, encompasses an enormous range of AI systems. Every chapter of the textbook can be thought of as instantiating this basic idea, which I call the standard model, in some particular context, whether it's goal-based planning or reinforcement learning or robotics. It all works the same way. There are many different subfields of AI. I think if you read the media, you would think that that AI is all deep learning, and deep learning is just one subset of machine learning, which is one method of getting AI systems to improve themselves over time. And it's become a common method of creating high-performing AI systems because of improvements in learning algorithms and the availability of larger data sets. But it's certainly not the only way of creating high-performing AI systems. And many of the systems that I'm going to talk about actually are not solely the result of deep learning. So the oldest branch of AI is problem solving, combinatorial search, constraint satisfaction, games. These are all areas that take the same basic assumptions about the world, that the world is discrete, that actions are discrete and predictable, and then uses some kind of combinatorial search to solve those problems. And that's been going on since the 1950s, beginning around 1960. Logic-based knowledge representation, reasoning, planning became popular. And around the same time, people started working on natural language understanding, using ideas from linguistics, such as grammars, parsing algorithms, lexicons, semantics, and so on. And then the interface areas of speech, vision, and robotics to allow AI systems to connect up to the real world. So there's tons of research going on in tons of different areas. It's an enormously broad field, but it's unified by this idea of defining objectives and then writing algorithms that optimize for those objectives. And our goal since the beginning has been to create what we might call general purpose AI. Some people call it human level AI, but that doesn't seem very ambitious. General purpose AI should be able to learn quickly in essentially any task environment to perform well. And that would include all the task environments where humans can function. But it will almost certainly include more than that, because AI systems have additional capabilities and characteristics that humans simply don't have. So the first question you might ask, if that's the goal, is what happens if we succeed? And oddly enough, we don't ask this very often. But I think one picture that people have in their minds is that if we succeed in creating general purpose AI, then we can use that AI to do anything that human beings currently do, and maybe do it well and do it extremely cheaply. And then use that to basically deliver what people need in their lives. And so one way of describing that would be that we could use it to lift the living standards of everyone on Earth to a respectable level. And we don't have to define exactly what that means, but the level that probably most of the people in this audience enjoy. And if we were to do that, so I arbitrarily took a figure at the 90th percentile of US incomes, then that would represent about a 10-fold increase in world GDP. And if you calculate the net present value of that, so the sort of the cash equivalent of that increase in global income, the net present value will be about $13.5 quadrillion. And compared to that number, that's the size of the prize, right? So these numbers that you hear bandied about, like, oh, the Chinese government is going to invest $150 billion in AI and so on. Those numbers are absolutely minuscule. They're not even in a rounding error compared to the size of the prize that we would win if we succeed in creating general purpose AI. And then on top of that, we may be able to do things better than we currently do. So this is just assuming we do what we already know how to do, except do it more cheaply through automation. But we could do things better. I think there's very little doubt that if we had general purpose AI, we could have far better healthcare, than we currently do. We could educate people individually, and we know that high quality individual tutoring is about 3 times as effective as classroom teaching. So typically we would expect kids to reach college level by the age of 10 or 11 under those circumstances. And perhaps we can actually accelerate scientific discovery, which has all kinds of benefits. So really, this is potentially the dominant technology of the future. And I've argued in other venues that success would be the biggest event in human history. And Alan Turing also thought about what would happen if we succeed. And everyone knows about his 1950 paper, Computing, Machinery, and Intelligence, which laid out many of the areas of AI and even proposed a strategy based on machine learning for achieving it. And that's largely an optimistic paper, and he's sort of rebutting a lot of skeptical attacks on AI. But in 1951, he actually talked about what would happen if we succeed. And he said, it seems probable that once the machine thinking method had started, it would not take long to outstrip our feeble powers. At some stage, therefore, we should have to expect the machines to take control. And he doesn't offer any solution or any apology, just resignation. This is just what's going to happen. So for the last few years, I've been trying to understand how this could happen and whether we can avoid it. So if we fast forward to the present, a lot of the things that Turing just speculated about have already come to pass. I just came back from a trip through Phoenix where you can actually take a taxi with no driver. We've seen the human Go world champions defeated by a program, something that many experts thought would take another 100 years before this was possible. This is some work from Berkeley, the global nuclear monitoring system that listens to the Earth for telltale signs of nuclear explosions, is now done by an AI system that's far more effective than what 100 years of seismology research had been able to achieve. This shows a little piece of North Korea where a 2013 nuclear test was located automatically by the AI system. We also are using AI for bad things. So just in the last month or so, we have seen reports of the first credible reports of autonomous weapons being used to kill human beings, as was predicted a few years ago in our little movie called Slaughterbots, which was widely derided at the time as just science fiction. Oddly enough, at the time that movie came out in late 2017, the weapon on the left, which is the Kargu drone, was released a month later by STM, the manufacturers in Turkey. So this is real, and people are already dying as a result. So I don't want to give you the impression that AI is now solved. In fact, I would say far from it. I'm largely skeptical that that deep learning is the solution to the AI problem or even the machine learning problem. I think it's a significant contribution, and there's still lots that we don't understand about why it works, and there's still lots we don't understand about why it doesn't work. But there's major breakthroughs that still have to happen before we reach human level or general purpose AI. So we have nothing that really understands language. We have a lot of superficial processing happening in these language models, but it's not clear that there's any real understanding there. The learning algorithms that we have are incapable of incorporating prior knowledge. But since they output knowledge, then until you have that capability, you don't really have cumulative learning happening. And that's essential for achieving general purpose intelligence. Human beings are capable of making plans over long timescales, years or even decades, as well as milliseconds. And we do this seamlessly. We integrate our thinking over all these levels of abstraction, and we have no idea really how to make that happen in AI systems. So there are several of these enormous conceptual breakthroughs that haven't happened yet. And it's very hard to predict when they're going to happen. So when I see these sort of quantitative predictions based on machine speeds or database sizes or anything like that, I think you have to take these with a very large bucketful of salt, because it isn't just a matter of making machines faster. If you make machines faster, you just get the wrong answer more quickly. So to get a sense of how unpredictable these things are, we could look back at the last time we invented a civilization-ending technology back in the 1930s. And at the time, we already knew, since the work of Einstein around 1905, that the atom contained an enormous source of energy. We could measure the mass defects between different atoms, and we knew how much energy would be released if we could effect this transformation that Rutherford is talking about here. So he is the leading nuclear physicist. Everybody asked him, can we get nuclear energy? And always he said, no. It is just moonshine, right? It's even 25, 30 years into the future, it's not going to happen. And this was a particular speech that he gave on September 11th to the British Association for the Advancement of Science. And it was reported in the Times the next morning. And Leo Szilard read the Times. He was staying in London and went out for a walk and invented the neutron-induced nuclear chain reaction. So this was less than 24 hours after Rutherford gave this speech. What Rutherford said was impossible turned into reality. And of course, we know what happened. Soon, the first nuclear bomb was patented in 1939 in France, and the first nuclear bomb was detonated in 1945. So I think it's prudent to assume that eventually, and the specific details of the timescale don't matter that very much, as long as it's not going to be like, next month or tomorrow. We have to assume that eventually AI systems will be making better real world decisions than humans. And that brings us back to Turing's point. It's our intelligence is what gives us power over the world. So we're creating more powerful entities than ourselves. How do we retain power over entities more powerful than us forever? Good question. And obviously Turing doesn't see an answer to that. But I think there is an answer, and to find it, we have to go back and look at the assumptions that we've made, and to look at this standard model of AI very carefully. Machines whose actions can be expected, sorry for that typo, can be expected to achieve their objectives. And this isn't just AI, this is several other disciplines, in fact, really all the disciplines that relate to decision-making. Control theory, you minimize a cost function. In statistics, you minimize a loss function. In operations research, you maximize a sum of rewards. In economics, you maximize a utility function or a welfare function. And in all of these disciplines, this has been very effective as a methodology. But we are starting to see that this methodology doesn't work because we cannot specify these objectives completely and correctly. So in economics, it's now well understood that trying to maximize GDP is not necessarily what you want, because, among other things, it leads to the destruction of the environment and enormous inequality and all sorts of other things. And so this is actually a message that we have known, a lesson we have known for thousands of years. And we could look back at King Midas, right? King Midas said, I want everything I touch to turn to gold. That's his objective. He got exactly what he asked for. And then, of course, this shows his daughter turns to gold, his food, his drink, and he dies in misery and starvation. And then, the sorcerer's apprentice bewitches the brooms to fetch water, but forgets to specify how much water, and then has to be rescued by the wizard. And if you find a genie who gives you 3 wishes, the 3rd wish is always, please undo the first 2 wishes because I've ruined the universe, right? And the problem is, with AI that's more powerful than us, there may not be even a 2nd wish. If we misspecify the objective, we are basically setting up a chess match between us with our true objectives for the future, our true preferences about how the future should unfold, and a machine that's now pursuing an incorrectly specified objective, which is in opposition, in some sense, to what we really want. And we don't want to be in that chess match. And this, I think, is really what Turing is expecting, that eventually the machines will take control simply because they're pursuing objectives that we have given them, but we have failed to give them objectives that take into account everything that we care about. And I would argue that we're already seeing the consequences of this type of mistake in the real world. So when you look at social media, the algorithms that control what billions of people spend hours every day reading and watching are designed to maximize one thing, which I'll call click-through. I mean, there are various other versions of this, engagement, and so on, but let's just take click-through as representative of the objectives that they use. So click-through is the probability that you click on the next thing that they send you. And I think originally when they designed these algorithms, they assumed that in order to maximize click-through, the algorithms would simply learn what people want to click on, which seems reasonable. But in fact, that's not the solution to the problem. That does not maximize click-through. What maximizes click-through is actually modifying people to be more predictable, because a person who's sort of middle of the road in their tastes and has sort of broad interests is very unpredictable as to what they're going to click on. And so they are less profitable than they could be if they were turned into someone who was very predictable in their taste, because then you could send them what you knew they were going to click on. So the algorithms learn one way or another to modify people to be more predictable. And I think that probably means more extreme in their views and tastes. And these are very simple algorithms. So this example, I think, illustrates a really important point, which is that when you don't have the right objective in the system, the better you make the AI, the worse the outcome is going to be. Because the system is more capable of messing up the world in order to achieve the objective that you stated. It's also going to be more capable of resisting any subsequent attempts to interfere, because interfering is just a way of preventing the machine from achieving the objective that you've given it. So it's not going to brook any interference. So instead of this approach, we actually have, I think, to do something different. And so this is what we started with, and I've argued that that's a mistake. And I think what we really should have done right from the beginning is not to assume that the objective has to be placed in the machine, but instead to say that what we want is machines that are beneficial to us, and sort of stop there, right? We want machines that are beneficial to us. What does that mean? That means that their actions can be expected to achieve our objectives. And of course, this is different because our objectives are in us. They're not in the machine. And this definition doesn't require us to specify the objective up front, fix it, and put it into the machine. It's a more difficult problem for the machine to solve, but this is what we would like. So let's see if we can do it. So this is just, in some sense, a restatement of what I just said, expressed in three principles, homage to Dr. Asimov, but slightly different principles from his. The first principle is that the robot's only goal is to satisfy human preferences. And so by preferences here, I don't just mean what kind of pizza you like, you mean your preferences over entire futures, right? Everything you care about, how the future should unfold. But the second principle is the key point, really, that the robot does not know what those preferences are. So it's explicitly uncertain about human preferences. And the third point basically sets up a grounding, if you like, of what human preferences mean. Human preferences are what leads to human behavior. And therefore, human behavior provides some evidence about what our true underlying preferences for the future are. And this third principle is not saying that our behavior perfectly reflects our preferences, that we always do exactly the action that's going to further our preferences to the greatest extent, because we don't, right? I mean, Lee Sedol, the Go player that I showed earlier, played moves in his games with AlphaGo that lost the game. That doesn't mean that he wanted to lose. It just means he wasn't good enough to choose the right action in furtherance of his preferences. So to interpret the evidence that our behavior, our choice behavior provides, requires some understanding of the human cognitive architecture. So I'll have a number of other caveats like that as we go forward. So I can translate these three principles into what we call an assistance game. And it's called an assistance game. It's called a game because it's a decision problem involving at least two entities, at least one machine and at least one human. And it's called an assistance game because the machine is set up to be of assistance to the human. In other words, the machine's objective is whatever the human's objective is, but the machine does not know what that is, but it still has to help the human achieve it. But we can actually solve these games. We can set them up mathematically, and we can calculate the optimal solutions to these games. Currently, we can only do very small ones, but in principle, we can do this. And we can look at what the resulting behaviors of the machine look like, right? When it's given such a game, solves it, and then carries out the solution. And it does what we hope. The machine will defer to human instructions. It will ask permission before doing any action that changes the world in a way that it's not sure we prefer, right? And so there's value in asking permission of the human so that it can be sure that it's satisfying principle one, satisfying human preferences. And in the extreme case, it will allow itself to be switched off. So this is, if you like, the core of the control problem. Can you switch the machine off? And we'll see, I'll show you why that machines solving assistance games will allow themselves to be switched off. And we can argue mathematically that it's in fact rational for us to build machines that solve assistance games. And that's really the argument why I think the new model is better than the classical model of AI, because it's rational for us to build these machines, and it's not rational for us to build the old kind of machine. And in this framework, as you improve the capabilities of the AI, it becomes better at learning our preferences and better at satisfying our preferences. And so we should get better outcomes rather than worse outcomes. So let me go into a little bit more detail about this off-switch problem, right? So here's our robot that we have in the lab, the PR2, and it's a big, heavy robot. It's actually about 200 kilograms. And so you want to have an off switch on this robot. And there it is on the back. It's actually legally required that there be an off switch, both on the machine and on a remote control button. But if you set up if you set up this robot in the classical way, you give it some objective like fetch the coffee, and if it's sufficiently intelligent, which is, we're assuming that it is, it doesn't take a genius to realize that you can't fetch the coffee if you're dead. So by giving it the objective of fetching the coffee, you are causing it to have as a sub-goal the objective of maintaining its own existence in order to fetch the coffee. And to do that, it will need to disable its own off switch to prevent anyone from interfering with this mission. And this is the kind of behavior that we want to avoid, right? We don't want machines to disable their own off switches and pursue blindly the fixed objective that they've been given. But when we have a new model robot, we'll see that it doesn't behave this way, right? And it's because of the uncertainty about the objective. So to show that, I'm going to actually go into a little bit of detail on how we formulate a simple model decision problem that reflects this opportunity for a robot to disable a soft switch. So in this simple game, the robot gets to go first and makes a choice. And initially, we just imagine that it has two choices, right? So one choice it has is to switch itself off, right? To actually press its own off switch, to commit suicide, if you like. And we'll fix the utility of that to be 0. So this is just setting an arbitrary scale where a robot committing suicide has value 0 to the human being. And then we're going, the robot has some other choice, which is potentially dangerous. Push this big red button, right? Maybe this big red button starts a nuclear war. Maybe it sets off all the sprinklers in the building, or maybe it does something useful. And by assumption, the machine is uncertain about the value of pushing the big red button for the human. And I've represented that over here on the left of the screen by a probability distribution on the utility of the action. So the x-axis is utility and the y-axis is how likely is it that the action has that utility value. So in this example, I've shown most of the probability is in the positive quadrant, which means that in expectation, the machine thinks that pushing the big red button is going to be beneficial to the human, but there's still a large potential downside for the action. Maybe it really does start a nuclear war. So if those are the only two choices, then the machine should push the big red button, which is sort of analogous to disabling its own off switch, right? It's going ahead with the action and not allowing the human to intervene. So we're going to have a third option, which is allow the human to intervene. In other words, allow yourself to be switched off. So we're going to now give the human a choice. So the robot could choose the wait, this third action, the vertical arrow down. Then the human gets a choice, and the human could switch the robot off. And again, that would have utility 0 for the human. Or the human can allow the robot to go ahead, in which case the robot will go ahead and push the big red button. Now, you might ask why, what's the benefit of the robot letting the human switch it off when it could do that itself, right? What possible gain could there be to letting someone else do something that you can already do for yourself perfectly well? If it makes sense for the human to do it, then you should have done it anyway. But the point is, the robot doesn't know if it makes sense for the human to do it, because the robot doesn't know as much as the human does about the value of the big red button. If the human switches the robot off, then in some sense, the robot learned that the big red button is undesirable. If the human lets the robot go ahead, then as the graph in the bottom left shows, the value of the action to the human is positive, because otherwise the human would have switched off the robot. So now it's safe for the robot to go ahead and push the big red button because it knows that this action is beneficial to the human. So this is a very, very simple example, but it illustrates a fundamental point, that the robot in this game has a positive incentive to allow itself to be switched off, because by waiting and giving the human that choice, it gains information. It gains certainty that the action that it was going to take is in fact beneficial. And it gains value from that, in the sense that it now has a plan, which is to wait and only push the big red button if the human lets it. That's provably better than the original plan of just pushing the big red button. But that's only true if there is uncertainty about what the human would choose. As soon as the robot is certain about what the human would choose, in other words, if the robot believes it knows the value of the big red button to the human, then the incentive to allow itself to be switched off disappears. So this second principle, that the robot is uncertain about human preferences, this is where we gain control over the machine. And we only lose, if all goes well, we only lose that control in the limit where the machine has become completely aligned with human preferences, right? Where it's learned enough about what we want that there's no residual uncertainty, and whatever it does is exactly what we would have wanted it to do anyway. A second theorem is that this robot is provably beneficial to humans, right? The expected value of the robot is non-negative to the human. So that's an important first step. So there's many, many extensions to this basic idea. And I'm sure that as I've been speaking, you've been thinking up complications, objections, and so on and so forth. So I'm going to go through a few of those. But the first set of complications has to do with the fact that there are many humans. And a machine making decisions on behalf of many humans is in some sense in the same position as, you know, a government making decisions on behalf of its people. And this question is at the core of moral philosophy and has been for thousands of years. A second set of questions has to do with the fact that there can be many machines in addition to many humans, right? And those machines may not all be produced by the same company, and they may not all be running exactly the same algorithm. So we have to be very careful that as we introduce more and more machines, even if they are designed in this provably beneficial way, that we don't get unanticipated strategic interactions that cause trouble, that cause like a flash crash on a global scale. A third set of issues has to do with the fact that humans are not perfect. So real humans have this imperfect connection from their true underlying preferences to their behavior. And so to get at the true underlying preferences, in some sense, you have to invert through a model of human cognitive architecture, which is a very complicated thing. So that's a huge issue. And economists have dealt with this. There's a whole subfield of economics called preference elicitation. They deal with this by only ever giving you completely trivial decision problems, like, you know, would you like an apple or an orange? And you say, I'd like an orange, and that's it. So they try to sort of finesse the whole human cognitive architecture thing by giving us choices that are so straightforward, we always do the right thing. So when I said earlier that the standard model of AI assumes that we have a fixed, perfectly known objective, I meant that very literally, that every chapter of the AI textbook begins with this assumption, whether it's a goal for search algorithms, or a set of constraints for constraint satisfaction algorithms, or a definition of a win for a game playing algorithm, or a definition of a reward function for a reinforcement learning algorithm. They all make this assumption. And so if we're getting rid of that assumption, we're going to have to rebuild each area of AI from the ground up. We're going to have to come up with new theoretical foundations, new algorithms, new practical technology, and that's a lot of work. And I think if we're going to convince people, you know, the Googles and Facebooks of the world, that they need to do things this way, we're probably going to have to actually build applications on this new foundation, and show that not only is this possible, but it's actually better, right? That these are the AI systems that you want. You don't want the old kind because they break in embarrassing ways and they have enormous risk of misbehavior that you really want to avoid if you're selling AI systems to people. So I'm going to briefly mention a few. Let's go a bit more deeply into some of these. So the real humans, we have to understand, as I mentioned with Lisa Doll, how are humans computationally limited? So how do our limited ability to compute, to examine possibilities and so on, how does that get reflected in our behavior? And then how do we go, invert that to see what people want, despite the fact that they're not actually acting in their own best interests. And I think one of the biggest ways that our cognition is limited is that everything we do pretty much is happening in the context of a deeply nested hierarchy of temporary commitments, right? So if you think about what I'm doing now, I'm speaking word, which involves moving my vocal apparatus. And that word is part of a sentence, and that sentence is part of explaining this bullet point. And explaining this bullet point is part of explaining this slide, which is part of giving this talk, which is a commitment that I made several weeks ago, and so on, so on, so on. So everything we do cannot be understood as, oh, Stuart's just doing the first action in the optimal plan for the rest of his life. No, I'm not. I'm giving this talk, right? It doesn't make any sense to think of me as acting optimally for my whole life. The only way we cope with the complexity of the real world is by organizing our behavior and making these commitments to sub-goals, which we then think about, and then we derive more sub-goals and so on down the chain until we actually do something. So we can't understand human behavior without understanding this hierarchy of commitments that people are engaged in. A lot of the things we do, we immediately regret. We call this emotionally driven behavior. So machines will need to understand when this happens. We don't even know our own preferences. So, if you'd ask me as a teenager, do I want to be a coal miner or a librarian? I might not know. It's hard for me to imagine how I'm going to react to each of those environments and how desirable, even if I can sort of imagine what that future would be, I can't imagine how much I would like it. I can't predict with certainty my own preferences. And so this is a really important part of interacting with humans. If you read anything in psychology, you will realize that our preferences are not an additive reward function, right? So it's not an infinite sum of discounted rewards. Things are much more complicated. They involve our memories of the past, our expectations about the future, our preferences for autonomy. So it's not so much what set of states do we drive the world through, but how much freedom did we have in doing that, right? Autonomy is a value in itself. A sense of agency is valuable to us, not just, is the world in a good place? And plasticity is probably the most important because if our preferences can change, which they definitely do, we're not born with our adult preferences. If our preferences can change, AI systems that are designed to satisfy preferences might change those preferences in order to make them easier to satisfy. So this is a real knotty problem that philosophers are just getting their heads around right now. And in particular, it's not even clear whose preferences you should try to satisfy, right? Because today I have preferences about tomorrow, and the machine is going to take an action that's going to affect tomorrow, but tomorrow I'm going to have different preferences about tomorrow. And so who should the machine naturally try to satisfy? Me today or me tomorrow? It's not clear. So there's still really deep work to be done on that. There are questions around decision-making on behalf of many humans. Probably the easier questions have to do with the fact that we all have different preferences. There's no sense here that there's one set of preferences that the machine is satisfying. There's no set of values that we're loading into the machine. There are 7.7 something billion humans. So we're going to have 7.7 something billion preference models. And the fact that those could all be different is completely fine. Doesn't cause any issues. And in fact, I believe that there's actually a lot of commonalities, which helps a lot, because it means that machines can be helpful to people that it hasn't met yet. Because it can reasonably expect that we will share a lot of preferences, like, we all prefer to be alive for the most part, and healthy, and so on. So machines can be helpful to people with even just a priori beliefs about their preferences. There are complicated issues about who exactly a machine should serve. Should it serve its owner? Should it serve everyone on Earth? If it serves everyone on Earth, then it's not going to spend much time helping you, mow your lawn or cook your dinner, because there are people who could benefit from its help much more than you. So it's going to go off and help them and leave you to make your own dinner, which might not be a very desirable commercial prospect. So we have to try to figure this question out. Actions affecting population size. So, these are real. The Chinese government, for example, took an action, which is the one-child policy, that probably vanished 500 million people from the future. Was that a good decision or a bad decision? It's a really hard philosophical question to understand how to make these trade-offs about the number of people who should exist. And if you've seen the Avengers movie with Thanos, right? So Thanos says, basically, here's my solution to this problem. If we had half as many people, they'd all be more than twice as happy. So he gets rid of half the people in the universe, right? And so that's his solution, maximizing global utility. We don't necessarily want AI systems to take that type of decision. So we really do need to get this right. I think I'll skip over some of these points. But I'll give a couple of examples for the last 2 points. So altruism, indifference, and sadism. So this is a set of questions that comes up in the utilitarian approach to combining the preferences of individuals. So this is pretty much what most AI researchers take for granted, and many economists, welfare economists, take for granted, that we should in some sense add up the preferences of the individuals when we have to make trade-offs, and choose the action that is most beneficial in the aggregate to a group of people who are affected. And we can understand an important characteristic of human preferences by dividing up our individual utility functions as human beings into 2 parts. One part being the self-regarding preferences, like, am I safe? Do I have enough to eat? Do I have a place to live? Am I warm? Am I comfortable? Right? And other regarding, right? Are my children safe, warm, and comfortable? Are my neighbors safe, warm, and comfortable? Are people in Australia safe, warm, and comfortable? Right? These are other regarding preferences. A simple model would just be to say we add these up, right? So if I have a world with 2 people, let's call them Alice and Bob, then Alice's utility is Alice's well-being, that's WA, and then some factor, CAB, the caring factor, how much does Alice care about Bob, times Bob's well-being. And then Bob's overall utility is Bob's well-being, and the caring factor, Bob, Alice, for Alice's well-being. And these caring factors are very important, right? If they're both positive, then that means that these are both altruistic people, that they at least care to some extent about the well-being of others. And that means they'll sacrifice, in some cases, a bit of their own well-being if that can give a significant increase in the well-being of the other person. Indifference would mean 0, so that you literally couldn't care less either way. And sadism would be negative, a negative caring factor. And this is the negative caring factor causes a problem, right? What should the robot do if the robot is now acting on behalf of Alice and Bob? Should the robot take an action that is influenced by the fact that Alice really wants Bob to suffer, right? That negative caring factor on behalf of Alice is going to shade the choice that the robot makes if the robot simply adds up the utilities of Alice and Bob. And many philosophers and economists have argued that in that case, no, we should, here's John Hassani, Nobel laureate in economics, no amount of goodwill to individual X can impose the moral obligation on me to help him in hurting a third person, individual Y. So basically saying if the caring factor is negative, then zero it out, ignore it, and don't take it into account. And I think that's a reasonable place where here is the AI researcher putting their thumb on the scale a little bit and saying, what is a moral principle? Now let's talk about something that looks quite different. Pride, rivalry, and envy. These are characteristics of humans that have to do with relative well-being. And economists, or sociologists, I guess, Thorsten Veblen and Hirsch is someone who brought this into economics with the notion of positional goods. So positional goods means things that have their value not from just their intrinsic characteristics, but their relative characteristics. So I have a nice house, or I have a nicer house than my neighbors. I have a bigger, shinier car than my neighbors, whatever it might be. Relative well-being is actually really important to people. And there's sort of two ways that it comes in. One is envy, so we can have an envy factor. How much does Alice envy Bob? Because Bob's well-being is bigger than Alice's well-being, right? So that's that term. And that envy makes Alice unhappy. And then there's pride. How much is Alice's well-being bigger than Bob's well-being? And that gives Alice pride. So that's a positive contributor to Alice's overall utility. Now, the problem with envy and pride is that you can rearrange this equation, and you see that both the envy coefficient and the pride coefficient end up being negative multipliers of Bob's well-being. So they function exactly like sadism. And if we were to zero them out, right, that would be a huge change, right? You think of sadism as sort of rare, perverse, fine, it's not going to be a big problem if we zero out sadism. But pride and envy, the pride you feel when your cricket team wins, right? That's a relative good because it means the other team lost. The pride you feel when you win a Nobel Prize is a relative good. It's a positional good because if everyone had a Nobel Prize, you wouldn't feel any pride about winning it. And so it's not the intrinsic value, it's the relative value. So this is incredibly important to people, and zeroing it out would have a big effect on society. And it might be good, but it's not something that I, as an AI researcher, I'm not ready to take that step. I think in the interest of time, I'm going to skip over these last 2 points and just say, if you're interested in any more details of these questions, there's a book on the left, Human Compatible, which is written for a general audience. So you can, there are a few equations, but they're all in the appendix, so you don't have to worry. Or the textbook, the 4th edition, has a lot of the new technical ideas, but unfortunately not all the chapters have been rewritten to reflect these ideas because we just don't yet have the algorithms and theorems and systems that reflect the new principles. So to summarize, I think that there's no stopping AI. The investment is already enormous. The potential is so much greater, and I think it's unstoppable. But if it leads to success in its traditional current standard model, then we will eventually lose control. And if you want to avoid that, I think we have to rethink the foundations of AI and rebuild in a different way. And I think it's possible to do. It's also desirable, right? These are the AI systems that we want. So there should be an incentive to do things this way. It's not just me wagging my finger at everybody. And so it's not really, I'm not really doing AI ethics and saying this is the ethical way to build AI. This is the good way to build AI. This is the right way. In the same way that if you build a bridge, it's not supposed to fall down, right? That's not an ethical way. It's not ethical finger wagging. It's just what counts as a good bridge if you're a civil engineer. And for an AI researcher, it should just count as good AI if it's beneficial to humans and not if it's not. So there's a couple of other problems, and many people are worrying, yeah, but what about the people who don't care? What about the people who want to take over the world, who will misuse increasingly powerful AI? And I think that's a real problem. And then what about overuse, right? What if we solve all these problems? We have wonderful AI that's incredibly helpful to us, that gives us, that lets us realize all of our dreams. Then what happens if we become dependent on it? What if we lose our own independent ability to function and become enfeebled in the way that is shown in Wall-E, that the humans have now no longer know how their own civilization even works? I think that's a very difficult problem, a cultural problem, not a technical problem, but something we should think about. Thank you.
Thank you very much, Stuart. Really excellent discussion. And there's a whole series of questions that have been coming in thick and fast through the Q&A session. And so I'm going to try and curate a couple of them. One of the discussion points is around this notion of human preference and whether humans actually understand their own preferences. But the question's also in the context of, do these intelligent machines of the future have the potential to preserve themselves, right? So this notion of a self-preservation, your red on button example, where the robot is in essence responding to something that is provably beneficial to the human. How do you protect against the robot's desire for self-preservation, perhaps at the expense of the human preference? So that's the first question. And then I'm going to ask the second question so you can just start thinking about these. The second question is a broader dialogue around this notion of AI for social benefit. You started with a statement around our objectives really around enabling the world to be better, increasing living standards, etc. And so that's prompted a whole series of questions in the Q&A around how do we really make that happen? How do we leverage some of the global inequities, for example, around income within the United States? Should we be looking at government regulatory frameworks as the EU is proposing? And so there's quite a lot of discussion here around responsibility from both a government and private industry perspective around enabling that socially beneficial piece. But it's also predicated on the first question, which is around this notion of, does the robot have a preference? And how do we ensure that it's really provably beneficial around human preference, or could the robot go out of control?
Okay, so I'll start with that, right? The notion of self-preservation. So the principles say there is no notion of self-preservation. So this is one of Asimov's laws that he got wrong. The robot should not preserve itself for any reason other than the first principle, which is being beneficial to humans. So if you've seen the movie Interstellar, the robot TARS at some point decides that if he commits suicide, that will help, that'll reduce the risk of the humans falling into the black hole. So he just commits suicide. And the humans are saying, no, 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 no. And he's saying, that's fine, please, don't worry, I'm off, right? That's the way, right? In fact, I think those are my favorite movie robots, is Interstellar robots. Partly because they're not humanoid, they're not made to look like people, but because they do the right thing when it's necessary. And so this is really important. If you put in any notion of self-preservation, then that sets up a conflict with human preferences, or potentially a conflict. So you don't put it in. It's not a problem. It doesn't mean that, the robots are all just going to commit suicide immediately, right? Because their reason for existing is to be helpful to people. So as long as their existence is helpful, then they will, they'll look after themselves, right? If it's distressing to people that they look all battered and dinged, then they will, tidy themselves up and so on, right? So it's nothing to do with self-preservation. In fact, It's the old way of thinking that we're going to give the robot some objective that creates this notion of I have to preserve myself in order to achieve the objective, right? And that that's an overly strong form of self-preservation that we don't want. I think tucked in there was another question: do we really understand our own preferences? I think that's a really important question. I did mention it briefly that we're uncertain about our own preferences, and it works out the way you would hope, right? So your uncertainty about your preferences sort of gets laid on top of the machine's additional uncertainty, right? So the machine doesn't even know about the preferences that you're sure about, let alone the ones that you can't know, the ones you're not sure about because it's unknown. And the kinds of behaviors that the machine would be, for example, to say, okay, if you don't know whether you like this kind of ice cream, here, why don't you try it, see if you like it, right? So I think if you want a very simple metaphor, it's not perfect, but I think it's helpful. So think about what happens when you go into a restaurant, right? Does the chef already know your objective function? Does he already know, or she already know exactly what you want to eat? No. Well, what does the restaurant do? They have a thing called a menu, and then you have a discussion with the staff about what's really good tonight, and and then they have a long wine list, and it's really hard for you to choose from. So they make suggestions, and you can try them, and so on. So there's a whole protocol that we learn for preference flow, right? And this is a key characteristic about this type of AI, is that preference flows at runtime. Right? There are information theoretically, there are bits of preference data that are flowing from the humans to the machines at runtime. And this is absolutely crucial. And to the extent that the machine can increase the flow of preference by asking questions or by having the human try something to see if they like it, then they'll do that. But I think, there's a deeper question. Do we really have preferences at all, right? Our brains are composed of multiple subsystems that, sometimes override each other, and maybe there's no notion of I to have preferences, right? With a sort of composite entity. And I think those are really important questions. But to the extent that, for example, I have conflicting preferences, there's literally nothing to be done. Right? If my own preferences disagree with each other, for example, if I have intransitive preferences, right? So I prefer, sausage pizza to plain pizza, and I prefer plain pizza to pineapple pizza, and I prefer pineapple pizza to sausage pizza. Now I've got intransitive preferences, right? They go around in a circle. Well, there's literally nothing the AI system can do to help you, because whatever pizza it makes for you, you're going to say, I like this other one better, right? So there's no satisfying some people, right? And that's a consequence. But there are really, then there's sort of societal scale version of that question. What constitutes a good human future? If we had a choice, right? If we sort of could snap our fingers and bring about the future that we all think we should have. We don't all think, right? We all have different views of what the future should be like. And almost all of us are wrong, right? We think we would like this, and then we get in and we say, oh no, this is terrible. So, but we are going to face this question, right? Mostly, for most of history, for most of humanity, you don't get to make a choice, right? It's, do I have enough to eat? And now, in some sense, collectively, the human race may reach a point, unless we really mess up, where we have a choice about the future. And we need some help. And then the other question, AI for good. So I completely understand there are practical questions about, even if we have this technology, how would we ensure that the benefits reach everybody? I think that's beyond my pay grade, so to speak. I think our political masters have much to understand. I think there is one thing working on our behalf, which is that, in a way, you can think of general purpose AI as basically an unlimited source of wealth. It's just a tap that you turn on, right? You're sitting there, in an isolated village. You need a hospital. You take out your cell phone, tap, tap, tap. A bunch of flying robots and rolling robots so arrive, and a week later you have a hospital. And so that tends to reduce the incentive for conflict, because no one fights over how many copies of the digital newspaper we have, right? I don't say, oh, you've got 10 copies, I want them, right? You don't, right? You say, well, just make some more of your own, right? It's easy. And so in that sense, it should help in defusing one of the main sources of conflict. I think there are still things we're going to fight about, because we can't make any more land, and we can't make any more of certain kinds of physical resources. So those things, I think, far-sighted countries are already thinking about. And I think everyone's going to have to figure out how to avoid conflict over those questions. But in the near term, there's a lot of talk about AI for good, and there's lots of very well-meaning, hardworking people trying to make AI beneficial. But to give one example, there's a couple of studies that came out recently. One of them in Nature Machine Intelligence. I think is actually from the main authors from Australia. And they looked at all the work in AI on trying to come up with useful diagnostic tools for COVID. And this was just a 10-month period, I think January through October 2020. And there were 2,200 papers published on this. And so what they wanted to know was, were any of these actually clinically valid and useful? And the answer was 0. Not a single one of those efforts met the required standards of quality to be clinically useful. And I think that's a sobering lesson, and it's our fault, because we are not, we're teaching people to do machine learning in a context where, getting 1% better on the Netflix competition or 1% better on ImageNet is sort of seen as the measure of quality. But in the real world, it just doesn't work like that. And there's a lot that we're not teaching. Obviously, there's a lot we're not teaching people about what do you have to do to make a difference in the real world, to make a system that really works. And just to give you one example, the global seismic monitoring system for the nuclear test ban treaty that I showed a picture of the North Korean example earlier. The AI part of doing that took about half an hour. And it took about half an hour because we happened to have a general purpose technology called open universe probability models that allowed us to just write down the solution in half an hour. It took about 3 months to implement it, get it working, running fast enough to operate on a global scale. It took 9 years to get it through all the committees. So, and I'm not saying that the committees were wrong, right? There's a lot of work. If you're doing anything high stakes like that, there's a lot of work in making sure that what you've done is correct and reliable and evolvable and maintainable and all the rest of those things. So, I think people are generally overestimating how easy it is to deliver useful AI in the real world. And so I'm not anticipating that, for example, AI is going to solve education or solve health or solve the climate. I think, you know, it can help a little bit around the edges, making certain kinds of tasks easier, but it's not a panacea that many people think it is.
Well,
at least not yet. It will be.
Thank you, Stuart. This has really been a tremendous discussion today. We're delighted that you were able to join us. It's been an absolute pleasure to host you today. We are going to wrap up now, and so a big thanks to all of our audience for joining us. You've been wonderful. Thank you for all the questions you've been asking. We've got many of them that we'll try and follow up on with you, but thank you for staying engaged throughout this lecture. We would like to encourage all of you that have joined us today to continue to participate in this upcoming series of events. You can join our mailing list by signing up through our affiliation program that's on our Monash Data Futures Institute website. We'd also like to encourage you again to follow us on social media at Monash DFI on Twitter and at the Monash Data Futures Institute on LinkedIn. Before we close completely here, I'd like to invite you to our next lecture in the Monash Prato Dialogue, which is on September the 9th, where we'll be hosting Professor Hugh Price from the University of Cambridge Leverhulme Centre for the Future of Intelligence. And Professor Price will be talking about the future of artificial intelligence and academia's role in getting it right. I really look forward to welcoming you again to these future lecture series. But before we end, Stuart, again, a huge thank you. It's been interesting, provocative, exciting, compelling, tremendous amount of feedback in the chat about how much people have enjoyed the session today. And so again, a big thank you from all of us at Monash University, the Monash Data Futures Institute. It's been a great event today, and thank you very much.
Thank you.
Goodbye, everyone.
Thank you for all the questions, and I hope to answer them at some point.
Yes, thank you, Stuart. Thank you. We really appreciate it. It's been wonderful. Thanks, everyone.